Ladies and gentlemen, welcome to machine learning. In this video, we will be talking about model selection and cross-validation. Let's jump right in. So in the last videos, we talked about how the bias and variance is influenced by the model's complexity. And now we want to ask ourselves, well, what is the best model? Well, how can we select the best models and what are differences in those models? Well, one difference, for example, is the degree of polynomial, where we, for example, in one case, we have just W0 plus W1 times X, where W's are our parameters. And in the other case, we have W0 plus W1 times X squared plus W2 times X to the power of 4. So these are two different polynomials. And we are interested, well, what of those is now the better model? And how can we compare different models? So one model is the linear least squares, for example, and one model will use neural networks that we will talk about later. So we have now a set of models, model 1, 2, 3, and 4, and we're interested, well, what is the best model of those? The first approach is very, very simple. We split the data. So we have now one section used for training, one section that will be used for model selection, and one section, model selection, and one part that is used to assess the final performance of the model. So let's plot our model. We have a train, we have a select, and we have a test. So we estimate the expected loss on the validation data set. So this is the validation data set to select the best model. And this is just the part for selecting the best model. The validation data set will not tell us anything about the expected loss of that model because we're adding basically we're biased when selecting that model. So to compute the final evaluation on the best model in the validation set, we use the test data set. But why do we need 3 data sets? So if we would have used the validation set to compute the expected error of our model, we will be biased because we use that already to select the best model. So if we have, for example, we have model 1, model 2, and model 3, we use the training data set to train it. Then on the validation, we will get an error of 0.1, for example, 0.3, and 0.01. So we see that on the validation set, our model 3 is the best one because it has the lowest error. But this is not a true representation because we select this model then and use it on the test set. And we will see that we get a 0.1, we get a 0.29, for example, and here we get a 0.05. So this is now the true accurate validation, the true accurate expected loss of our data if our test set is large enough. So we need 3 data sets so that the final model evaluation of this model is not used in neither selecting our model. So this is actually not done at all. So it's just like that. So we're selecting the final model with the validation set. And now we introduced a bias into that validation set. And to get rid of that bias, we will need the unbiased estimate. And that is of the training set. In the training phase, we train it with the training set and select it then with our test set. So now the question is, well, how do we split the data? Because we only have a finite amount of data, and we want, on the one hand, we want the largest data set for the training, so we can get the best parameters because we lower the variance with that. But on the other hand, we want a correct estimate, so our test set needs to be as large as possible. So the bigger the validation set, the better our expected value, the better our estimation of the error on the validation set will be. However, increasing the validation data set will decrease our training data set and our test set because the total available data is limited. So decreasing the train data increases the expected loss, because the expected loss increases with less data because of the variance. So now we have again the dilemma. We want to know, if we want to know how good the model is, so actually increasing our validation data set, the model has to be worse because it has less data to train on. But if we use more data to train on, our expected, so our value of the expected loss is not accurate enough because we don't have enough data in that validation data set. So this is the trade-off that we have to understand. How can we get rid of this problem? One option is cross-validation. So this is basically a clever approach that we can use both train and validation data for training and still have a good enough estimate for our expected loss. We do that such that this is our data, and we use this part. So we section off our data. For example, this is all the data we have, and we section it off into 10 parts. So we use 9 out of 10 those sections for training and only 1 for testing. And this will give us a test error. Then for the next run, we use again 9 out of 10 sections, but we ignore the second one. So we train on the first and 3 to 10. And sorry, this is the third. And this is the second one. We use the second for the estimation of our error and so forth till we use each section for validating our model. And we will get 10 errors. And then we average those and get the average prediction. This is also called k-fold cross-validation. And we can do that also for each model. So if we have multiple models, we can do that multiple times and get an accurate prediction of our expected loss. And the algorithm is like this. So we split our data into k disjoint subset. So data points that are here are not in the other data points, in the other sections, and they have to be roughly equal size. So we say that if we have, for example, 1,000,000 data points and we just use 10 of those sections, we will have, or let's actually make it 1,000,000. So then we will have 100,000 for each section. So then we select one model and we do the whole process. So we withhold the first data set and train on all the other, the first section and train on all the other. Then we use the validation error of the, on that model from the section that we withheld. And after we did that for one model, we compute the average of those expected errors. So this will be our validation error, which is the average over all errors. And we do that for each model. So if we have 10 models and we have 10 sections, we have to perform 100 trainings. And in the end, we can just simply choose the best model and retrain it on the whole data set. We could just simply say, well, if our model was the best already with 9 out of 10 data sections, we can just leave it at that and save one training phase. Or we can say, well, this is very important to us because we increase the data by around 10%. So if we have k is equal to 10, and we will get an even better prediction when we push our model to production. So how do we split the data again? So here we said that if k is 10, this is the typical choice. We call it tenfold cross-validation. If we say that we leave only one data sample out of our process, we call it leave one out cross-validation. So if we have our x's and y's, so we have x, 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 and so forth. This is 1, 2, 3, and 4. And this is y1, y2, y3, and y4. Before we had sections, but now we leave one out. So we only take one data point and test on one single data point. So we will have much more data to train on, but we also have to run this algorithm n times as many data points as we're having in our data set. So the disadvantage of this cross-validation is the computational costs, because we have to do it over and over again to then average over our predictions. I hope this video gave you a better understanding on how we work with those models. So let's summarize. We talked about the model selection and the cross-validation. We have multiple models that can differ in the degree of polynomial, hyperparameters, or the method that we actually used. We proposed a first approach with the train, validation, and test set, but we said that this is very expensive regarding the data. We said that, well, why do we need 3 data sets and how we split the data, and that we have a dilemma that each part wants to have as much data as possible. As a solution to that, we introduced cross-validation, where we divide the data into chunks and train all the chunks except one and compute the error on that chunk and change that chunk multiple times and average over the expected loss and get an accurate prediction. That this is called the cross-validation, where we also compared the different models. So we can do that for one model and we can do that for many models and get an accurate prediction of our expected loss. And we talked about how we can split the data, where we have the typical choice of k is equal to 10 or the very, very expensive case of leave one out cross-validation. If you have any questions, feel free to ask them in the comments down below. Thank you very much for your attention, and I'll see you in the next video.